Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, Tifr, Jest, IIT-Jam and other exams related to physical science. Okay. So this is the lecture number 11 of condensed matter physics. Okay, so in which I'm going to discuss specific heat. Okay, and also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay, and also I would request you guys, please share my detail to your friends as well, so that they can also uh, watch free live classes of mine and get benefited from it. Okay, so let's get started. So specific heat we are going to study. specific Specific heat. Okay, specific heat we are going to study. So in solid, okay, so we have solid. So there are two specific heats is made of two things. Okay, that is electronic 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 specific heat, electronic specific heat. Okay, and the second is uh, specific heat because of lattice vibration. Okay, so lattice oblique phononic specific heat. So there is two specific heats in solid. That is, one is electronic specific heat and lattice or phononic specific heat. Okay, electronic specific heat is because of free electrons in the material, and okay, and the lattice and phononic specific heat is due to lattice vibrations. Okay, so now we can write Cv, the specific heat of solid. Cv solid is equal to Cv because of free electron plus Cv because of Cv because of this one, lattice. Okay, so this Cv of solid is Cv because of free electrons and Cv because of lattice vibration. Okay, Cv lattice. This is important point. Next is that in turn. So experimentally, we have found lattice specific heat. Okay, lattice specific heat. Lattice specific heat, guys. Okay, so experimentally we have found Cv, that is specific heat. Okay, is proportional to T cube at low temperature. Okay, and Cv is constant. We have find constant at high temperature. At high temperature, that's what we have found experimentally. Okay, experimentally. Okay, so Cv is proportional to T cube. So lattice specific heat I'm talking about. Specific heat due to lattice vibration. Yeah, lattice specific heat. Cv is proportional to T cube at low temperature and Cv equal to constant at high temperature. This we have found experimentally. Okay. Very important point. Next, we'll find CV theoretically, okay, and let's see which will match with experimental values, okay. Next, there are three specific hits which we are going to study, okay. Theory for specific hits, okay. First is classical theory, okay. Classical theory, classical theory, okay. Classical theory. That is also called Dulong-Pettis theory. Okay, Dulong-Pettis theory. Dulong, Dulong-Pettis, Dulong-Pettis theory, or we can say Dulong-Pettis law. Okay. Uh, we also say Dulong-Pettis law, but it's a French word, guys. Okay, so its pronunciation is, especially for men, the T is silent. Okay, so that is why we call it Dulong-Pettis law. Okay, so this is Dulong-Pettis law. Okay, so in this theory, what is said? Atoms, atoms of, let's say, atoms of solid, yeah, they do simple harmonic oscillations. Okay, simple harmonic oscillations. Okay, atoms, simple harmonic oscillations. Okay, simple harmonic oscillations. Atoms do simple harmonic oscillations. Okay, and so they are simple harmonic atoms are simple harmonic oscillators, and they do simple harmonic oscillators. And next point is given, that is vibrates. Atoms vibrate. Atom vibrate with atoms vibrate with same frequency. Okay, same frequency. So these are the points for classical theory. It's a Dulong-Pettis law. Okay, so in this theory, it is said that atoms do simple harmonic oscillations and they vibrate with same frequency. Okay, and in 1D for one atom, in 1D for one atom, energy is, we know that is energy is, that is T plus B, T plus B, right? Kinetic energy plus potential energy. So 1D for one atom, one harmonic oscillator, it is going to be Px square upon 2m plus half Px square for simple harmonic oscillations, right? And and average energy is going to be, this value is classical value of this kinetic energy is half kT, and potential energy is also half kT. Okay, so this value is half kT, half kT. Okay, half kT means that value is going to be kT. Average energy value is going to be kT, guys. Okay, kT. Average energy is going to be kT. Okay, now in 3D, this value is going to be in 3D. In 3D, in 3D, average value of E is going to be 3 kT. Okay, 3 kT, because in 1D it's kT, right? 3 kT, 3 kT. Okay, so average value of this is that simple harmonic oscillators is 3 kT. Okay, so then CV value, CV we know, del average E upon del dt upon dE upon dt, right? Average E upon dt. This is the value. Important formula, guys, you need to note down. Okay, d average E upon dt. This is CV. So we'll put the value. So CV is going to be, this is d upon dt into 3 kT, and this value is going to be, and because for n atoms we are talking, for n atoms it is going to be 3n kT, 3n kT, okay, 3n kT. So this is going to be 3n kT. Okay, this is for n atoms, okay, n classical atoms, 3n kT, and this value is going to be 3k, 3nk, 3nk, 3nk. Okay, since nk value is r, right? So this value is going to be, so this means value of CV is going to be 3r. Value of CV is going to be 3r. Okay, 3r. Okay, and that is constant at all temperature. That means CV equal to 3r implies constant at all temperature. Okay, and that's why, and this is not the case, right? Experimentally we have found the value, so that is constant only at high temperature, right? So that implies this theory fails for low temperature. Okay, this theory fails because at low temperature the CV is proportional to T to the power cube, right? T cube. So this theory fails for low temperature. This theory fails for low temperature. Okay, next, second is, so quantum theories for specific heat, right? Quantum theory for specific heat. Quantum theory for specific heat. Okay, so there are two theories are given. That is, one is Einstein's theory and second is Debye theory. Okay, we discuss both. Okay, so first is Einstein theory. Einstein theory. Okay, Einstein theory. Okay, so in this theory, it is considered atoms are quantum harmonic oscillator. Okay, quantum harmonic, atoms are quantum harmonic oscillators. Atoms are quantum harmonic oscillators, and they vibrate with quantized frequency. Okay, vibrate with quantized frequency. Okay, okay, so Einstein theory, Einstein considered atoms as a quantum harmonic oscillators. Okay, and considered they vibrate with quantized frequency, guys. Okay, quantized frequency. So and whose energy is given, that is En equal to, for simple harmonic oscillator, that is quantum harmonic oscillator, n by 2 n plus half h cut omega. Okay, this is En, where n equal to 0, 1, 2 and so on. Okay, quantized frequency. Okay, and average energy for the oscillator is given by, for one oscillator, that is h cut by 2 plus h cut omega upon e to the power h cut omega upon kt minus 1. Okay, so this is for one oscillator, one quantum oscillator in energy, average energy in 1D. Okay, so h cut by 2 plus h cut upon h cut omega by 2 plus h cut omega upon e to the power h cut omega upon kt minus 1. Now for 3D, n oscillators, for n oscillators, for n oscillators in 3D, this E is going to be, I'll write in next page. So E is going to be 3n h cut omega by 2 plus 3n, n are the molecule, okay, number of molecules for n atoms, number of atoms, okay, for n oscillators in 3D. So this is going to be 3n h cut omega upon e to the power h cut omega upon kt, e to the power h cut omega upon kt minus 1, kt minus 1. Okay, so this is the average energy for n quantum oscillators. Okay, so now we'll find cv value. We know how to find cv is de average upon dt, right? So this is if we do it, then value of cv is going to be, that is 3r theta e upon t whole square, theta e upon t whole square, e to the power theta e upon t, e to the power theta e upon t upon e to the power theta e upon t minus 1 whole square, guys. Very important problem. Okay, this you need to note down, this one. So value of cv is going to be 3r theta e upon t whole square, e to the power theta e upon t upon e to the power theta e. So this is cv equal to 3r theta e upon t whole square into e to the power theta e upon t upon e to the power theta e upon t minus 1 whole square. Okay, so this is very important. This is the specific heat according to Einstein's theory, guys. Okay, where theta e value is h cut omega upon k. This is Einstein temperature. This is called Einstein temperature. Einstein's temperature or Einstein temperature. This is called Einstein temperature. Einstein temperature, okay, h cut upon k, that is theta e. Okay, now we'll study different cases for this CV. Okay, case number one. Case number one is at high temperature. At high temperature. At high temperature, we can see omega h cut is less equal to kT. Okay, less equal to kT. Then CV is going to be 3r theta e upon t whole square e to the power theta e to the power theta e to the power theta e upon t e to the power theta e upon t upon this one. Since this is here, well, I'll explain. Since h cut omega is less equal to kt, right? So, and we know x value is h cut omega upon kt. This is the value of x. Okay, and so, and here we can see this is less equal to this, means h cut omega upon kt is going to be less equal to 1. Okay, this value h cut omega upon kt, this value is going to be less equal to 1, right? So this value is x value is very less, right? Very, this means this value less equal to 1. So it means e to the power x is going to be almost equal to 1 plus x, right? So we'll open it. So this is going to be 1 plus theta e upon t minus 1 whole square, right? 1 will get cancelled, this will cancel with this. So CV value is going to be here, this will get cancelled, right? 3r into e to the power theta e upon t. Okay, so this is the value of CV. So this implies value of CV is going to be CV is going to be equal to 3r. Okay, CV is going to be 3r. Okay, because this value is very x value, this h cut omega kt is less equal to 1. Okay, so that's why very less value. So CV value equal to 3r. So so you can see it is valid at high temperature, right? This is this one. Right. CR. Now we'll study case 2. Case 2 is case 2 at low temperature. At low temperature. At low temperature, h cut omega is going to be greater equal to kt, right? In that case, CV is going to be 3r, this value, right? We are using case here, right? This is the value of this one. This is the CV. Here we are writing it. This is for at, this is the value of CV, right? According to Einstein theory. So this is going to be 3r. Okay, and theta e upon t whole square e to the power theta e upon t upon, this is going to be at low temperature, because h cut omega is greater equal to kt, right? So this is going to be e to the power theta e, because then it's a very great value, means e to the power theta e upon t value is very good, because we know since theta e equal to h cut omega upon k, right? So this value is going to be e to the power theta going to be e to the power theta e upon t whole square, right? One we will ignore because this h cut omega value is greater equal to KTO. So e to the power theta e upon t is very great value, so we can neglect the value 1, right? So if we solve it, so this value CV is going to be equal to 3r, right? 3r theta e upon t whole square and e to the power minus theta e upon t. Okay, this one. So this will it is going to be e to the power 2 theta e upon t. This will go in numerator. Then value is going to be e to the power. This value is going to be e to the power minus theta e upon t. So from here you can see CV is proportional to e to the power minus theta e upon t. CV proportional to e to the power minus theta e upon t. Okay, this is the one. This is the case 2, CV, value of CV. Okay, in case of Einstein's specific heat theory. Okay, so this is the value of CV at high temperature. Sorry, at low temperature. My apology, at low temperature. At low temperature. Okay. Okay. Next is Debye theory. Okay, Debye theory. Debye theory. So in this case, what Debye has considered, all atoms oscillating, all atoms oscillating in a lattice, oscillating in a lattice, all atoms oscillating in a lattice and coupled with each other. Okay, all atoms oscillating in a lattice, which are oscillating in a lattice and coupled with each other. Okay, they are coupled with each other and coupled with each other, coupled with coupled with each other, coupled with each other. So all atoms oscillating in a lattice and coupled with each other. Okay, so they are oscillating and they are coupled with each other. Okay, all atoms are oscillating. Okay, all atoms are oscillating in a lattice and coupled with each other, and they are coupled with each other. Okay, so their frequency of vibration, their frequency of vibration, their frequency of vibration cannot be the same. Frequency of vibration cannot be the same. Cannot be the same. Okay, so all atoms oscillating in a lattice coupled with each other, they are coupled with each other. So because of that, their frequency of vibration cannot be the same. As in classical mechanics, it is supposed that the frequency of vibration of harmonic oscillators are same, but here not, because they are oscillating and as well as they are coupled with each other. So that's why the frequency of vibration cannot be the same. Okay, so and CV is given in Debye. CV is given. CV is given, that is 3r theta d upon t fd. Okay, this is very important formula, guys. You need to note down. Okay? Cv equal to 3r Cv equal to 3r Cv equal to 3r theta d upon t into ft. Okay, where theta d is Debye temperature. Okay, theta d is Debye temperature, and fd is Debye function. Okay, fd is Debye function. Fd is Debye function. Okay, and value of fd is important, guys. Okay, 3t upon theta d 3t upon theta d to the power 4 integration 0 to theta d, my apologies, 0 to theta d 0 to theta d upon t x to the power 4 e to the power x dx upon e to the power x minus 1 whole square. Okay, so this is the fd, Debye function, guys. Okay, so this is fd equal to 3t upon theta d to the power 4 integration 0 to theta d by t x to the power 4 e to the power x dx upon e to the power x minus 1 whole square. Okay, so this is the Debye function, guys, and where this is theta d is Debye temperature, and value of theta d is equal to h cut omega d by k. Omega d is Debye frequency. Okay, omega d equal to Debye frequency. Okay, and this is Debye temperature, the h cut omega d upon k, Debye frequency and Debye temperature. Okay, where okay, and x value, this is, we know x value is h cut omega d, that is Debye frequency upon kt, right? Value of x is okay, here x is okay. This is the theta d value. Okay, and omega d is Debye frequency. Okay, and this is Debye temperature, and this is the Debye function, and this is very important formula you need to note down. Okay, Cv equal to 3r theta d upon t fd, and fd value is that 3t upon theta d whole square integration 0 to theta d upon t x to the power 4 e to the power x dx upon e to the power x minus 1 whole square. Okay, well, this is Debye. Next is we are going to study different cases. Okay, case 1, at high temperature.